Hello everyone, welcome to the lecture of this course heat transfer. So this is the continuation of the last lecture of this module mass transfer. So in the last lecture we have discussed in details the Fick's law in case of the diffusion. And there we have seen that this Fick's law it is analogous to the Fourier's law of heat conduction and Newton's law of viscosity. So that Fick's law it has been discussed in details, and the different formula related to this Fick's law we have seen those, and different numericals based on those Fick's law formulas we have discussed. So today we will be discussing the general mass transfer equation in case of a stationary media. After that we will see the mass transfer coefficient formula and different correlations related to the convective mass transfer, and based on those different relations of convective mass transfer we will discuss some numerical in this lecture. So let us start this lecture. So first we will discuss this general mass diffusion equation in the stationary media. So in case of the conduction heat transfer, there we have discussed the general differential equation for the heat transfer. Now this general differential equation of the mass transfer for any species, it can be derived on the similar process that we have seen while deriving the heat transfer equation. So this type of diagram we are familiar with, which we have used while deriving the heat transfer equation in one dimension and three dimension cases. So in that similar manner we can derive the general mass diffusion equation in the stationary media. So here we need to actually consider a homogeneous medium consisting of binary mixtures of species A and B, which you can see here. The medium will be stationary, so that means the mass average or molar average velocity of the mixture it is 0, and the mass transfer it can occur only by diffusion. So after that, this differential control volume dx dy dz, which we can see in this diagram, it has been considered. And after that we need to consider the mass balance equation along the x, y and z direction. Then the mass influx and mass outflux equations we need to form. And after that, in the mass balance equation we need to put this mass influx and mass outflux relation along the x, y and z direction. So if we perform this procedure, then after several steps we will get this final form of the mass transfer equation in case of the stationary media. So it is del 2 Ca del x2 plus del 2 Ca del y2 plus del 2 Ca del z2 plus NAG by DAB. This is equals to 1 by DAB del Ca by del tau. So it can also be represented as delta square Ca. This is equals to 1 by D delta Ca by del tau. So this is actually analogous to the heat conduction equation. So what is this NAG? This is actually the rate of increase of the mass of species A due to the chemical reaction per unit volume of the mixture. So this is the NAG. So we need to only remember this mass diffusion equation here. Next, let us discuss the steady state diffusion in some common geometry. So the steady state diffusion through the plane membrane we will discuss here. So in this diagram we can see the diffusion through a plane membrane. One plane membrane has been considered here, and we have considered the mass diffusion of fluid A through this plane membrane, and its thickness is capital L, which is very small in comparison with the other dimensions, that is the mass diffusion through this membrane can be considered as one-dimensional. Now, the mass concentrations of the fluid at the opposite wall faces, that is C1, Ca1 and Ca2, in the bottom and top faces, this has been considered the mass concentration as Ca1 and Ca2. Now, considering the diffusion along x-axis, the controlling equation we can write as del 2 Ca del x dx2, this is equals to 0. So this relation we have got from the mass diffusion equation. So yes, here in this case of a plane membrane, we have considered the diffusion only along the x direction, so that's why we have neglected all the other parts and we have only used this d2ca dx2, this is equals to 0. Now upon integration, this dca dx, this is equals to c1, and if we integrate this one again, then we will get ca equals to c1x plus c2. Now we need to use some boundary condition to get the values of the C1 and C2. Now what are these boundary condition? The CA equals to CA1 when x equals to 0. So this one we can see from this diagram that CA equal, when x equals to 0, in that case the CA, this is equals to CA1. So that is in the bottom part of this plane membrane. And when x equals to L, then in the upper part of this plane membrane, in that case the CA equals to CA2. That means C2 equals to CA1 and C1 is equals to CA2 minus CA1 divided by L. So these are the values of these integration constants we are getting putting the boundary conditions in the equation number 1. Now if we put these values of C1 and C2 in the equation number 1, then we are getting the mathematical representation of CA. This is equals to CA2 minus CA1 into x by L plus CA1. Now the mass transfer rate can be calculated as ma by a is equals to minus d dca dx, so which is the fixed law of diffusion. So this is equals to minus d to d dx of the value of Ca. Now we have entered here Ca2 minus Ca1 into x by L plus Ca1. If we do the differentiation, then we are getting this actually minus d into Ca2 minus Ca1 divided by L. d dx of Ca1, it will be 0. Now ma by a, this is equals to my d by L into Ca1 minus Ca2, or ma by a, this is equals to Ca1 minus Ca2 divided by L by d. Now this L by d, this is known as the diffusional resistance. So in case of heat transfer, we have discussed the thermal conduction resistance, the concept of this resistance part in case of thermal conduction, then convection, and for radiation. For all these three different modes of heat transfer, those resistance concept, it has been discussed. Now in case of this mass transfer, again we are getting this diffusional resistance, which is the L by D in case of this steady state diffusion through a plane membrane. Now this equation number 13.34, which is ma by a equals to d by L into Ca1 minus Ca2, it gives us the mass flux through the membrane. Let us discuss one numerical based on this formula. A steel rectangular container having walls 16 mm thick is used to store gaseous hydrogen at elevated pressure. The molar concentrations of hydrogen in the steel at the inside and outside surfaces are 1.2 kg mole per meter cube and 0 respectively. Now, assuming the diffusion coefficient for hydrogen in steel as 0.248 into 10 to the minus 12 meter square per second, calculate the molar diffusion flux for hydrogen through the steel. So this is the numerical given here. We need to calculate the molar diffusion flux for hydrogen. Now let us first write what are the things given in this numerical. The length of this wall, that is the thickness, actually it is given as 16 millimeter, that is 0.016 meter. Then Ca1, it is given 1.2 kg mole per meter cube, the molar concentration for the hydrogen. The steel, and in case of the inside surface, it is given 1.2 kg mole per meter cube, and in case of the outside surface, it is given 0. Next, the diffusion coefficient, in this case it is given 0.248 into 10 to the minus 2 meter square per second. So to calculate the molar diffusion flux rate, that is NA, which is actually MA by A, we need to use this formula from the Fick's law of diffusion. So MA by A, this is equals to dA into Ca minus Ca2, that is Ca1 minus Ca2 divided by L. So the value of dA, it is actually given in this numerical, that is 0.248 into 10 to the power minus 12. And the value of Ca1, which is the molar concentration of hydrogen in the steel at the inside, so it is given 1.2, and Ca2 it is given 0, which is at the outside. And the L, which is the thickness, it is given 0.016 meter. So putting all these values, we can get the molar diffusion flux. This is coming as 18.6 into 10 to the power minus 12 kg mole per second meter square. So this is the procedure by which we have calculated the molar diffusion flux for hydrogen through the steel. Now earlier, while discussing the Fick's law of diffusion, we got one terminology, that is diffusion coefficient. Now let us discuss what is the mass transfer coefficient. This mass transfer coefficient H suffix mc, it is similar to the convective heat transfer coefficient H. So this convective heat transfer coefficient we have discussed while discussing the convection part. There we have seen the rate equation for the convective heat transfer coefficient. It is H, which is actually we are getting while discussing the Newton's law of cooling. So in case of this Newton's law of cooling, we have seen that Q equals to H A into the temperature difference. So this H is the convective heat transfer coefficient. Now this mass transfer coefficient HMC, it is similar to this convective heat transfer coefficient. So for species A, this MA, that is the mass transfer coefficient, it can be written as dA into Ca1 minus Ca2 divided by x2 minus x1. So this is equals to HMC into A into Ca1 minus Ca2. Now this HMC, this is the diffusion mass transfer coefficient of species A based on concentration difference. The unit is meter per second. So the mathematical representation of this diffusion mass transfer coefficient, this is d by x2 minus x1. Here the A is the cross-sectional area meter square, and Ca1 and Ca2, these are the fluid concentrations at the two faces. Now the mass transfer coefficient can also be expressed in terms of the partial pressure differences for the species A. So how we can represent this mass transfer coefficient in terms of the partial pressure? So Ma equals to dA into Ma by gt into, using the partial pressure terms, that is Pa1 minus Pa2 divided by x2 minus x1. So after several steps, we are getting that Ma equals to HMP into A into Pa1 minus Pa2. So this HMP is equal to HMC into Ma by GT. So this is HMC divided by RT. So this HMP, it is the mass transfer coefficient in terms of the partial pressure differences. And this HMC, it is the mass transfer coefficient. the species. So this is the relation in between the two different mass transfer coefficient considering the partial pressure and only one species. So this HMP, this is equals to HMC divided by RT. Now for diffusion of water vapor through a layer of stagnant air, we can write MW, this is equals to HMP A into PW1 minus PW2. So here we have used the mass transfer coefficient in terms of the partial pressure. So after that we can write this equation number 13.73, where the mass transfer coefficient based on the pressure differences HMP by rearranging the earlier step. Now the corresponding expression of mass transfer coefficient based upon concentration difference, it can be written like HMC equals to dP by x2 minus x1 into Pw1 minus Pw2 into ln P minus Pw2 by P minus Pw1. So these are some representation of the mass transfer coefficient in terms of the partial pressure and pressure differences, it is HMP. Then the mass transfer by convection, it involves the transportation of material between a boundary surface and a moving fluid, or between two immiscible moving fluids. So this mass transfer by convection, it can be expressed like Ma by capital A, this is equals to Hm into delta Ca. So this M suffix A divided by capital A, it is the mass flux which occurs in the direction of decreasing concentration, and Hm, this is the mass transfer coefficient of the component A. Now let us discuss some correlation for the convective mass transfer. So earlier we have seen the different correlation in case of the convective heat transfer. So let us now discuss the some correlation for convective mass transfer. So the equation for conservation of momentum and energy for the boundary layer development on a flat plate, this has been written here: U del S plus V del U del Y, this is equals to nu del to U del Y2, and U del T del S plus nu V del T del Y, this is equals to alpha del 2T del Y2. So these equations we have seen while discussing the Navier-Stokes equation in case of the boundary layer. So similarly, the concentration equation may be written like U del C del X plus V del C del Y is equals to capital D del 2 C del Y2. Now here C, it is the concentration of the component which is diffusing through the boundary layer, and capital D, it is the diffusion coefficient. Now different dimensionless parameter we need to use here. Like first one, it is the Prandtl number. So this Prandtl number, it is familiar to us. So this Prandtl number, it is equals to nu by alpha. So it forms the connecting link between the velocity and temperature profiles. These profiles becomes identical. These profiles become identical when this Prandtl number, this is equals to 1. Next dimensionless parameter, this is equals to the Schmidt number. Now this Schmidt number, this is equals to nu by d. So it forms the connecting link between the velocity and concentration profile, and these profiles are identical when the Schmidt number, this is equals to 1. Next dimensionless term, it is the Lewis number. This Lewis number formula, it is alpha by d, and again it forms the connecting link between the temperature and concentration profile, and these two profiles become identical when this Lewis number this is equals to 1. And lastly we are having the Sherwood number. Now the Sherwood number formula this is equals to hmc into x by t. So this is a function of Reynolds number and the Schmidt number. So these are the four different dimensionless terms we are getting in case of this convective mass transfer, which are the Prandtl number, Schmidt number, Lewis number, and Sherwood number. So these formulas of this four dimensionless terms these are required to solve the numericals based on this convective mass transfer concept. Now there are different empirical relations based on this correlation of the convective heat transfer. So first case it is the flow over a flat plate. The local mass transfer coefficient for laminar and turbulent boundary layer flows past a flat plate oriented at zero angle of incidence. It is given by the Sherwood number SHX. That is the local Sherwood number. This is equals to hm into x by t. And this representation is 0.332, Reynolds number to the power 0.5 and Schmidt number to the power 0.33. So this it is actually similar type of representation which we have studied in case of the studying the Nusselt number correlation in case of the convective heat transfer. Next, in case of the turbulent flow, the Sherwood number it is equals to hmx divided by t. So the representation is 0.0288, Reynolds number to the power 0.8 and Schmidt number to the power 0.33. So these two representations are applicable for laminar flow and turbulent flow respectively. Now in case of the average values, these values will be doubled. For mixed boundary layer conditions with transition occurring at a critical Reynolds number of Reynolds number equals to 5 into 10 to the power 5, then the correlation in terms of the Sherwood number, this is 0.037L Reynolds number to the power 0.8 minus 870 into Schmidt number to the power 0.33. So these are the three different representation of the Sherwood number when the fluid it is flowing over a flat plate. Next, in case of the flow in tubes. So in this case, when the fluid is flowing in tube, then Gilliland proposed the following correlation for forced mass convection through a tube. And the representation of the Sherwood number it is 0.023, Reynolds number to the power 0.83 and Schmidt number to the power 0.44. Now this relation it is applicable when the value of Reynolds number it is in between 2000 to 35 into 10 cube, and the Schmidt number it is within 0.6 to 2.5. So these are the different formula and the representation of Sherwood number in case of a flow over a flat plate or flow inside a tube. Again, some formula are applicable for laminar flow and some are applicable for the turbulent flow. So these formulas we need to remember to solve the different numericals. Let us discuss these numericals. Air at 1 atmosphere and 25 degrees centigrade containing small quantities of iodine flows with a velocity of 6.2 meter per second inside a 35 millimeter diameter tube. Calculate mass transfer coefficient for iodine. So now some thermophysical properties are given here, that is nu, it is kinematic viscosity, this is 15.5 into 10 to the power minus 6 meter square per second. And the diffusion coefficient it is given 0.82 into 10 to the power minus 5 meter square per second. So here we need to calculate the mass transfer coefficient of iodine. So to calculate the mass transfer coefficient of the iodine, we need to first determine which formula of the Sherwood number we will apply or use here. So for that we need to find the value of the Schmidt number and Reynolds number, because based on their limiting values, the mathematical representation of the Sherwood number, it gets changed. So first, the formula of the Sherwood Schmidt number, this is mu by rho d. So this is actually nu by d, because this nu kinematic viscosity equals to mu by rho, that is dynamic viscosity by density. So you can write the formula of the Schmidt number. This is equals to nu by d. So this nu and d, these two are given in this numerical. So the value of Schmidt number we are getting is 1.89. After that, the formula of the Reynolds number, it is known to us, it is ud by nu. So it is actually the ratio of inertia force by viscous force. So u is given here 6.2 meter per second, d is given 0.035 meter, and nu, that is the kinematic viscosity, is given 15.5 into 10 to the power minus 6 meter square per second. Putting all these values, we are getting that the value of Reynolds number, it is 14,000. Now, from this value of Reynolds number and Schmidt number, we can say that the flow is turbulent, and that's why the mathematical representation of the Sherwood number that we will use here, it is Sherwood number equals to 0.023 into Reynolds number to the power 0.83 into Schmidt number to the power 0.44. So this is the relation that we have discussed in the earlier slide, that when the Reynolds number that we are getting here, this is 14,000, which is in between this range given, and the Schmidt number range is also matching here, it is 1.89. So this formula, that is flow in tube, it is proposed by Gilliland. So we will use this formula of Sherwood number, which is 0.023, Reynolds number to the power 0.83, and Schmidt number to the power 0.44. So putting the value of Reynolds number and Schmidt number in this formula of the Sherwood number, we are getting the value of Sherwood number is 84.07. So we have calculated the value of Sherwood number, but we need to actually calculate the mass transfer coefficient of iodine. So the formula of Sherwood number, it is actually Hm into d by small d divided by capital D. Now from this relation of Sherwood number, we need to calculate the value of Hm, which is the mass transfer coefficient. So Hm can be rearranged in terms of Sherwood number. So it is Sherwood SH, the Sherwood number, into d, capital D divided by small d. The value of Sherwood number, it is known to us, 84.07. Then capital D, it is the diffusion coefficient given in this numerical, and small d, it is the diameter of the tube, which is 35 millimeter. So putting all these values in the formula, we have calculated the value of this mass transfer coefficient, which is 0.0197 meter per second. So this is the procedure to solve this numerical. We need to first calculate the value of Schmidt number and Reynolds number, and based on those values we will determine, or we will identify, that which formula of Sherwood number will be applicable for that specific numerical. Let us discuss the next numerical. It is given air at 20 degrees centigrade and 40% RH flows over a water surface at a velocity of 1.4 meter per second. Length parallel to flow is 200 millimeter. If average surface temperature is 16 degrees centigrade, then calculate the amount of water evaporated per hour per meter square of the surface. Now some data are given here. For partial pressure of water vapor at 20 degree and 40% RH PWA, it is given 0.011 bar. The vapor pressure at 16 degrees centigrade and saturated PWS, it is given 0.017 bar. Viscosity of air, that is dynamic viscosity mu, it is given 16.38 into 10 to the power minus 6 kg per meter second. And air density, it is given 1.22 kg per meter cube. And the diffusion coefficient, it is given 0.256 in 10 to the power minus 4 meter square per second. These are the data given in this numerical. We need to calculate the amount of water evaporated per hour per meter square of the surface. So first we need to calculate the value of the Reynolds number. Now the value of the Reynolds number is inertia force by viscous force, that is mathematically represented by UL divided by nu. So that means the Reynolds number, this is we are getting as 1.85 into 10 to the power 4. Now as this value is less than 5 into 10 to the power 5, so the flow it is laminar. Now the mass transfer coefficient we can use, you can calculate using the Sherwood number value, that is 0.664 into Reynolds number to the power 0.5 into Schmidt number to the power 1/3. So the value of the Sherwood number we are getting ultimately 75.846. Now from this value of the Sherwood number we can write the formula, it is Hm into x divided by d. So from this formula we can calculate the value of this mass transfer coefficient, which we are getting as 0.00971 meter per second. Now to calculate the concentrations, that is the density, we can use this formula, that is concentration at temperature Ta, that is Cwa, it is Pwa divided by R into Ta. So using this formula the concentration, we can calculate the Cwa, it is 0.00813 kg per meter cube. Again the concentration at temperature Ts, it is desaturated, we can, it is T surface, we can calculate Cws, this is 0.0127 kg per meter cube. Now the mass diffusion of water, it is given by mw equals to hma into Cws minus Cwa. Now putting all these values of the mass diffusion of water, we have calculated the final value of the mass diffusion for water, it is 0.1596 kg per hour per meter square. So these were the procedure by which we have solved these numericals. So we need to solve all this type of numerical, we need to first identify the value of the Reynolds number and Schmidt number, and based on their limiting values we will use that specific relation of the Sherwood number. And after that, this formula of Sherwood number, this is equals to hx by d, from which we need to calculate the mass transfer coefficient. Okay, so today we have discussed this general mass diffusion coefficient, general mass diffusion equation, then the steady state equation for the plane membrane. After that we have seen the mass transfer coefficient formula and different dimensionless terminology we have seen, like the Prandtl number, Lewis number, Schmidt number and Sherwood number. And after that, in case of flow over a flat plate and in case of a flow inside tube, we have seen four different equation for the Sherwood number. And based on this different relation of Sherwood number, we have discussed two different numericals today. So this is the end for this lecture.